Welcome back to the lecture series on GPU architectures and programming. So, if you recall, we have been discussing different possible GEM optimizations. For example, we started with the basic GEM, right. The first optimization was just pushing in our normal tiling concepts, right. So, how the idea of tiling helps in matrix multiplication when done with shared memory based tiles. But then we also saw that that leads to a small amount of compute with respect to the loads, and that can be further improved. So, all that we did was we coarsened the threads, and in that way we could actually reduce the ratio of compute. I mean, we could actually reduce the ratio of load with respect to the computes, and we to say in other words, we actually were able to increase the amount of compute per load, right, by doing the coarsening optimization. And then we exploited the wider load engines that are available in NVIDIA GPUs, because they do not support vector operations like multiply and add, which is vectorized, but they actually provide you with wider load and store instructions. So, we made good use of this float 8 kind of data types here for kind of using our tiles with I mean using the wider load instructions for filling in the tiles. That is how we will put it, but that also required us to go through this complex switching of values, which we have already explained in the last lecture, right, how to support the wider data types and all that. But the next thing that it comes is called what we call as rectangular tiles. So, we will just do a brief recap like why that is required. So, in the rectangular tiles part, if you remember that K40 GPUs have got this 48 KB of shared memory, right, whereas for this tiles that we have defined, they were 32 cross 32 tiles, 2 of them each storing 4 bytes of data. So, it was overall 8 KB. So, that is like the basic reason that why you want to have a rectangular tile, right. Now, well, what do we do with that? So, let us just browse through this idea of rectangular tiles once again. All that the idea was pointing to is that since we have a large amount of shared memory, so we can increase the tile size, and that is what we did, right. So, we increased the tile size from 32 cross 32 to tiles of size 64, right. So, that is what we discussed, that well, we will increase the rectangular tile size, and but then there was also this optimization that since we are supporting bigger tiles, why not also store the matrix B in a transposed way, because then you have the advantage of load memory access coalescing while loading from the global memory. But then we also figured out that well, that leads to a problem with the shared stores. For that we needed to flip the indices here, so that the shared memory stores are done in a nice way, so that they can be fetched again properly. But that also led to a problem that when I am now looking for loading from the shared memory, they are all falling in the same bank. So, in order to reduce this bank conflict, we padded the data here, right. So, that is a short summary of how rectangular tiles were really helping us, right. So, these were the changes, like you do global loads from B, where B is pre-transposed, and then you do shared store through the matrix B sub in such a way that the load is optimized here, and the way you optimize the load is you pad the data types here with two elements, because in each bank you have memory width of 64 bits for the loads. So, you pad with two positions here, and that gives you a huge advantage over the baseline of implementations. Now, let us just start with the next optimization, which is what we call as 2D register blocking. So, just to remember that in case of rectangular tiles, we had to do I mean the transpose and then store properly in the shared memory while doing the untranspose in the local from the local memory, right, and then we had to pad the data here. So, these are the three things which we needed to do simultaneously. Now, again coming to the register blocking part, well, we have earlier been discussing the optimizations where we are kind of doing the coarsening, I would say, in one dimension, right. Because if you remember, while we are doing thread coarsening, we are computing for multiple data points in one dimension. When we are supporting wider loads, again we are doing a similar coarsening in the other dimension, right. So, the general idea could be that you increase the work per thread in both the row and column dimensions, right. So, this is what we call as 2D register blocking. So, essentially we are doing the register loads in such a way that it's essentially similar to 2D tiling that we discussed for the shared memory based optimization for matrix multiplication, but this is done at a different level. So, that means let us just replicate the idea that you are doing a shared 2D shared 2D load of data from the global memory to the shared memory. Let us just replicate the idea and load data in a similar way from the shared memory to the global memory, right. So, that is what we will be calling as 2D register blocking. So, it is similar to 2D tiling, but it is done at a different memory level. In the earlier case, it was from the global memory to the shared memory. In this case, it is from the shared memory to the registers, right. So, what really helps here? The optimization is that it helps to reduce the shared memory traffic. Just like using the earlier optimization of normal standard tiling, what we are really doing we are really optimizing the global memory of chip traffic. So, in this case, you are using the same idea between shared memory and the register file to reduce the shared memory traffic. So, let us just have a look at how it works. So, we will just use our usual definitions. The tile size in dimension m, remember that we are multiplying m cross k and k cross n matrices here, right. Tile size in dimension n and then tile size in dimension k, this is what we set. And then if you remember earlier, we were defining work per thread while doing coarsening. We will just use the same idea in the in terms of work per thread in dimension m and work per thread in dimension n, right. So, if we are trying to coarsen the work in both these dimensions, then we will have a reduced tile size in both the dimensions, right. So, these are tiles which will be based on the shared memory for loading data to the registers, right. So, then the reduced tile size in dimension m would be just like the tile size in dimension m divided by the amount of work we are now giving to a single thread in dimension m, right. So, it is just tile size in dimension m, you divide it by the work per thread that we are now trying to define in the same dimension. So, that gives me this RTS m. Similarly, I can have an RTS n, right. So, that is essentially nothing but TSN by the work per thread that I have defined in the dimension n, right. So, once this is done, then I can define that what is the amount of data load that each thread has to do for A and B matrices. In our case, in this simplistic case, we will consider for two of them that to be same here. So, LPTA A is nothing but the overall tie size for the m cross k matrix divided by the reduced tile size in the dimension m multiplied by the reduced tile size in the dimension n, right. So, that gives you the loads per thread for A. Similarly, what happens to loads per thread for B? Well, you consider the original tile size in dimension k and tile size in dimension n for the matrix B, and you divide it by the reduced tile size in the dimensions, right. So, essentially you are dividing the original tile size by the reduced tile size, and that is giving you the amount of loads that a thread has to do for A, and similarly the amount of load a thread has to do for B, right. So, since this TSM and TSN are considered to be equal in our case, so for us the loads per thread for the matrix A, LPTA and LPTB, the loads per thread for matrix B, they are going to be same, right. So, with this we can then go and define the blocks and the thread, the grid and the blocks, right. So, they can be as just like this, that so I am dividing m by TSM, n by TSN, that would be my DIM3 definition of blocks, and similarly for threads, right. So, what will be my basic steps when I am going to execute this 2D register blocking? So, of course, one thing is to be sure that I am increasing the work per thread further by using this optimization. For identifying the threads, we use for each thread we will initiate these following local variables. So, let us say I define this TIDM and TIDN just for noting down the local thread IDs with respect to the columns and the rows, right. And of course, the maximum value each of them can have will be this TSM divided by WPTM, and similarly the TSN divided by the WPTN, like we have defined earlier. Okay. And similarly, we can compute the offsets which will be used soon, like exactly from which block the thread shall start working. To figure that out, you multiply this tile size in the dimension m with the block ID for the thread, and similarly the offset in the dimension n can be found by the tile size in dimension n multiplied by the block ID in the y dimension, right. So, the next thing that comes is, well, we have to define the memory to fit a tile for A as well as a tile for B, right. So, how do you really do it? Well, we already have these TSKs and TSMs defined. So, that gives me the A sub as TSK TSM and B sub the other memory as TSN TSK plus 2, if you remember our earlier idea of the padding that we have to introduce here, right. So, that is actually getting carried over here. So, the next thing that of course, you have to do is, well, you have to initialize a 2D accumulation register here. Earlier it was a 1D array, but now since it is a 2D register blocking. So, you are initializing this ACC in a 2D array with all zeros for the float values, right. But then comes what is the overall operation that you have to do for per thread for every tile. So, this is your number of tiles, right. So, overall the k, and you divide it by the TSK, that is your tile size in the k dimension. So, that is the total number of tiles you have in that k dimension over which you have to hop, right. So, this is the tile loading loop, the outer loop of the multiplications, right. So, this gives you the number of tiles, and inside this you have the same older steps to be done for this newer setting, that you have to load one tile of A and one tile of B into the shared memory, and then you have to loop over the values of a single tile and perform the computation just like earlier. Only thing is, you have more work per thread right now, and at the end of the entire computation, when all this load and compute for all the tiles is done, you just write back the values in the result matrix C, right. So, here comes the load part. So, how do you really load? So, of course, one may just start thinking that, well, I have got this 2D data to load, but we will do it in a single loop here. The way we are doing it is, as you can see, for each position I am just iterating from 0 to LPTA, right, the load per thread value. So, this is the amount of data I am supposed to load, and since LPTA is equal to LPTB. So, just by iterating over this loop I can do the loading for the both the A sub and B sub matrices. And from where am I supposed to load? Well, we are representing all the threads in the first and second dimension by one global variable ID. So, let us understand, I mean, what is the problem here. So, we have already defined the work per thread, but now, I mean, ideally one may start thinking that, well, this would be a 2D loading. So, why don't I have a cascade of two loops for doing the loading? Instead of that, what we are doing is, we also know that how many loads one thread is supposed to do, right. So, let us just iterate one loop from 0 to that maximum number of loads that the one thread is supposed to do, and figure out a global position for each thread. You figure out a global position in the array from where you are supposed to do the load. So, that essentially we are trying to figure out by computing an ID, right, and then so that position I can just figure out because I know the m and what is the offset inside it, and then I can go to the corresponding row, right. So, by computing these values I can just figure out from where to load, right, and then the other thing I will do is I will figure out the ID of the thread by using this local computation. You can just easily check that how this ID is getting computed, and if you just do a percentile and a divide operation, you can just find out what is the row and column index in A sub and B sub where you are supposed to put the value, right. Mind that your A sub and B sub have the opposite things, because for B you are having the transpose matrix, right. So, it is just like the previous case here, we would say, Yeah, so B sub always has this in rows, same thing. So, using this loop, you are just identifying here through this access expression from which location in the matrix A you are doing the load, from which location in the matrix B you are doing the load, and by doing this computation of ID with this formula, you can just check it up, because you are just figuring out which numbered load, and then you are multiplying it by this reduced tile size to go to that corresponding location, right, and then you are just doing an offset with the TID which you have already computed here, right. So, with this you are able to go to the locations of both I mean in the of the A and B matrix both, right. So, again we will just repeat that here we compute the tile index, right, and then you are just multiplying the tile index with the m and n, because these are the corresponding dimensions to look for in the A and B matrix, right. Mind that B is transposed here. So, because these are the dimensions to look for in the A and B matrix, and then from A and B you are doing a load to A sub and B sub, just like we have discussed earlier. So, the variable ID that we have which we have computed here, you are just then doing these two operations to figure out what is the row and column value where to load, right. Once the loading is done, you are going to run this computational loop where you are actually going to perform the multiplications, and for that what you do is, this is your outer loop. Then for inside the outer loop, first notice that the outer loop is definitely going to run for k values, right, up to TSK, right, that is the tile size in k, right. And then because again the next tile will load, and again you are going to run this for TSK, and that's just like how you do computation with tiles, as we all know about. So, then the thing that you do is you cache the values of B sub in the registers. Now, that is an important step. So, observe what is going on. So, you have got this value of B sub. Now, you are going to load them in this array B reg. Now, why is this important? Observe that B sub is shared, right. So, it is in the shared memory, but where is B reg? B reg is a local array, which means this will be located in the register, right. So, you are now going to cache these values of B sub that you have the consecutive values, right. So, you are just computing this column index, right, for the same k, you are just computing this column index and getting the value from B sub, and you are loading it into B reg, right. So, in that way, with this loop you are loading all the values of B sub that you require for the multiplication in B reg. Well, what is the next step? So, this actually caches all the required values for B sub, and then now you get to the computation. So, now for the real multiplication computation, you have this for loop where you are running it for this WM0 to this work per thread for M, right. And here what you are going to do is, well, first you compute the row index from using this TIDM and this WM values, and that gives you the exact value from A sub which is going to be multiplied. Well, so as you can see, you are essentially caching a single value of A sub into the register, and that is the value that is going to be multiplied with all the values of B reg continuously and stored in the accumulator, right, for the corresponding value. So, this we are not repeating, because as you can understand, this follows the similar pattern like our earlier optimizations, right. You need all the consecutive B values, but you need this single A value, right. That is why you have already cached these B values, right. So, as you can see, this is all the work for one thread, right. So, the real multiplication by the thread is really happening here, right, and since you have two loops, so in that way you are getting a quotient set of values done, right. So, if we just repeat inside C, so this is your C, you have got these tiles defined. For one tile, well, these are the reduced tile sizes I am drawing. For one thread, you are now making that thread do a 2D computation. So, this loop is actually iterating over the number of computations that is to be done, right, work per thread in M, and then in one direction, of course, right. Of course, you have this A and B, so, this outer loop is going over the work per thread in direction M, and the inner loop is going over the work per thread in direction N, but for a single position of this direction M, you load one array value, right, and for that you are going to use these BREG values, right, this sequence of BREG values. So, in every outer iteration, what you are doing is you are caching a single value, right, and then in the inner iteration you are going to use this array value with this array of BREG values, right. So, what is important to note is that, well, every thread has got some per thread activity. For every thread, for each tile you have got some per thread activity. So, if you see, this is per thread activity for a thread in one tile, right. So, for that single tile, what you are really doing is you are first figuring out, well, for this tile what are the values I am supposed to load, and you are so this is where the threads loading of values from the shared memory to the registers are getting done, right. So, that is why we have it like cache the values of B sub in registers, right. So, here inside this compute loop there is some amount of memory activity going on. The memory activity, to be more specific, is for loading values from the shared memory to the registers, and this is what we would say is the crux of the optimization. Like earlier we have already seen this optimization, right, which is like loading from global mem to shared, and next the current optimization is when you load from shared to a 2D register area, right. So, that is what you do. So, as you can see, inside this loop, in for one value of k, you are first making a sequence of loads in from this B sub, right. So, you are making a sequence of loads from this B sub to here, right, and then so that is the activity for this thread, and similarly for the other threads also they are all making their own corresponding caching of values of B sub for this loop, right, and for this thread, after it has got these values cached, it goes to perform the real computation, right. So, where what it does is inside this for loop, well, first it performs the computation of the row index, then it uses the row index to compute, well, what value is to be loaded into array for the corresponding A sub shared memory, right. For that it has got this index, right, which row and k is getting computed, and then here it is keeping it constant and multiplying it continuously with these BREG values, right. So, it is multiplying this array continuously with BREG values and it is iterating here over this. Well, once this is done, again it will load from the outer loop, it will again load another corresponding value of from A sub to array, and then again in the inner loop it will multiply this array value with a sequence of values from BREG, and that is how it will work. So, with this we have the computation done in 2D, and once this is done, the next thing is loading it back to a global memory. So, for that, well, first you have to figure out what is the location where it has to be loaded, and again as you can see, since this will be this is a 2D activity, like this thread is going to again load back a 2D area of values, right, for one thread. So, what it does, again you have a cascade of 2 loops, and it figures out that what is the global position where it has to do the load. So, that is figured out by first computing a global row from the outer loop, and then in each iteration of the inner loop it figures out a global column value, and this combination of global column and global row is used to figure out a position in the C matrix where this value from ACC has to be written back, right. So, this is how the final values get stored in C. So, this is our idea of how these different possible optimizations can be performed for doing the GEM computation. So, just to recall, all we do here is that we are using our earlier optimizations together, but doing it in a 2-dimensional way by coarsening the threads in both dimensions. Well, here we have not used the wider load idea, that is also something you need to understand, right. But the important thing is for you to figure out that how the computes work, like as I am giving a 2D amount of computation to be done for each thread, that is why now I have a cascade of loops here for doing all those computations and also the loading of the data. And as I recall that there are two levels of loading. Here you have a load going on from the shared memory, from the global to the shared memory, and then in your earlier compute loop you now have an amount of load first done from the shared to the registers, and then you and these two steps we are now kind of differentiating here, and then I am using the cached values to multiply with, I mean I am caching a single value of AREG and multiplying it with a sequence of values of BREG and so on and so forth through this loop cascade, right. And then again I am storing it back using another loop cascade. So, right now I have more work per thread, and this is a good optimization in the sense that in modern GPUs you have big, I mean sufficiently big shared memories, and so if you can just choose a proper tile size and a suitable thread coarsening factor in the 2 dimension, then this can really help. Okay. So, the summary here would be that GEM is the most computational heavy kernel which is used for fully connected layers and also the convolution layers of neural network, and the optimized implementations that we have discussed so far, they focus on the training phase of course. And if we are speaking about the other phase of neural network work like inferencing, so that refers only to a forward pass over a trained neural network, and so in general these optimizations we have discussed will likely be more important for HPC kind of places where you, because you are primarily going to do large neural network training in such such kind of I mean significantly powerful computers, whereas inferencing is the more popular workload for embedded GPUs, because in an embedded GPU you can have an inferencing engine for doing lot of stuff like recognizing somebody's image from a camera, or doing some object detection, or maybe live streaming a video and from that doing a face detection and all that. Those are inferencing kind of works. So, they also require different kind of optimizations which you can figure out. So, with this maybe we will like to close this current lecture. Thank you.